I'm gonna take you with me on one of my most precious diving memories. It's one of those memories that still, years later, hangs fresh in the mind to be reminisced upon with a smile. I was younger then, still a relatively new diver with only a few trips under my belt. I was still diving with my parents, and life seemed simpler in a lot of ways. Our newest obsession at the time was the Cayman Islands, a vibrant community with so much to see. Grand Cayman hosted beautiful beaches and colorful metropolitan festivals. Cayman Brac set our adventure against the backdrop of dramatic coastlines, cliffsides, natural caves, and abundant wildlife. And Little Cayman, the quiet sibling, was small and relaxed, the perfect getaway to distract the mind from the stressors of life, whatever the troubles of a young teenage me might have been back in those days. There was so much to experience, but linking all three of the islands, beneath sparkling and turquoise waters, was the diving. Beautiful, vibrant reefs and pure white sand, dramatic walls and deeper, craggy dives. With so much to explore across the islands, every dive offered something new. This particular tale isn't one of heart-racing adventure. It was found none too far from shore. It wasn't a deep dive either. It was shallow, perfectly lit in the Cayman's afternoon sun. With rays of light beaming through the azure waters, the colors of the reef burst forth in an ever-moving flurry of life. This particular vibrant and dazzling reef just so happened to be structured to be easy to navigate. This enabled us to branch away from the main dive group and still find our way. Long lines of reef stretched out perpendicular to shore along the shallow, sandy bottom, almost like fingers stretching away from your palm. Before we knew it, we were enchanted by this meditative dive as we swam parallel to the shoreline, cresting over coral into a valley of sand. Over coral into sand. It is in this relaxed state of near transcendent zen that I made a friend. Curious about the clunky and inefficient swimmers blowing bubbles in their domain, the mottled amber shell, graceful, playful flippers, and gentle, adorable face of a sea turtle appeared. In this moment, we were alone with the turtle, hidden from the rest of the world so far away. Now, I'd seen turtles before, but it had been fleeting or far away. But this turtle intentionally swam close enough to see its friendly and curious eyes. It swam next to me as we hung at the same depth, somehow exchanging thoughts and feelings with another across the barriers of both language and species. If rule number one of diving wasn't to always keep breathing, I would have been breathless. I took many photos of this incredible animal, whom I later identified as a hawksbill turtle, and we turned to continue our dive. We had had our moment, and we were ready to leave it to being a wild animal, doing wild animal things. But be it out of curiosity, boredom, or maybe even playfulness, the hawksbill actually followed. We swam over coral and sand, and the turtle kept close, sometimes ahead, sometimes behind. Over or under each other we swam. We swam together for what must have been at least 5, maybe 10 minutes, though in the rush of the moment it felt much, much shorter. About the time we needed to turn the dive around to get back to the boat, we said our final goodbyes, and I watched as my new friend swam off into the distance, vanishing from view and breaking the enchantment. We finished the dive as we had planned, but the day couldn't get any more perfect. You know, I still think about that turtle a lot. It doesn't have a name, and it's been years, but just that memory of one turtle is incredibly impactful. In science, and especially conservation, we tend to talk a lot about population levels. Whole ecosystems, numbers this and numbers that. Endangered, critically endangered, least concern. But something gets missed when we talk about these incredible animals as mere statistics. We miss a connection that's inextricably more human. I feel that we miss that impact of an individual. Sure, it's important to talk about the statistics, the science, and what we are doing to protect these animals, but it's just as important to talk about the animals themselves. What makes them different from us, but also what links them to us. The turtle that I encountered that day was just one turtle among many, but that one turtle had a story. It had years of life filled with experiences of struggles past and victories won. A story not dissimilar to my own, though perhaps the character arcs are just a bit different. So today, as we begin talking about the subject of these amazing animals, I invite you to consider them through both lenses. From the perspective of the inquisitive scientist, but also from the viewpoint of a human being, who, despite our many differences from these aquatic reptiles, may not be so different from them after all. So grab your mask, slip on your fins, and calibrate your lab instruments. Let's descend. Hey there! You're listening to Season 2 of Bio-DIVE-rsity, the podcast about pelagic paradigms and coral curiosities, where we bring the best in flippin' fun fish facts straight to your ear holes. It's like we're the delivery drivers of peer-reviewed aquatic science, the Grubhub of fish food for your mind, the DoorDash of dope decapods. Here on the show, we examine the weird, wacky, and wonderful diversity of life that lives under the sparkling waters of our blue home. Using cutting-edge science as our guide, we dive deep into both the common and the rare, the exotic and the ugly. So tune in for the turtles, stick around for the Cyphozoans. Let's descend. Today on the show, sea turtles. Man, who doesn't love turtles? They're cute, graceful, and generally just a joy to be around. Since that amazing hawksbill experience, I've had a number of other close encounters with these beautiful reptiles, and each and every one has been unique and awe-inspiring. You know, it's kind of nice. This time I don't think I have to convince anyone that this episode's animal is cute. And that's, of course, thanks in no small part to aquariums, documentaries, outreach facilities, all around the world where sea turtles are the star of the show. I mean, kids and adults alike love seeing them swim through the water, often accompanied by placards or volunteers giving the turtles names, personalities, and even stories. You know, often the turtles on display in such places are rescues, animals found in distress in the wild and brought into the facility for rehabilitation, with the eventual aim of re-release back into the wild. As of a 2019 review here in the US, there were 42 different facilities or agencies permitted to conduct sea turtle rescue, rehabilitation, relocation, and release. And with just a little digging, you can find a plethora of personality, with both heartwarming and heartbreaking stories to keep us both enraptured and engaged. There are turtles that are found cold-stunned and freezing, having drifted into waters far too cold for them. They had to be slowly and painstakingly warmed degree by degree. There are turtles struck in unfortunate boating accidents, who have to be nursed back to health with the trauma of a damaged shell. From turtles found panicked and tangled in ghost nets to those with stomachs full of plastic, there seems to be no end to these disheartening tales. Eventually, though, with enough luck and enough care, these turtles will share in the success story of rehabilitation and re-release back into the wild. But Even beyond the touching stories of these brave turtle individuals, the storybook of sea turtles as a whole is packed to the brim with wonder. This is, of course, because they are innately wondrous animals, with incredible and well-adapted anatomy, awe-inspiring navigational skill, and even just a little mysterious intrigue. But maybe we should take a step back and examine just what a sea turtle even is before diving into all of that mystery and excitement. So, across both land and sea, there are around 356 different species of turtle, and only 7 of those are classified as sea turtles. Sea turtles differ from their land, marsh, and river siblings in many ways, but the primary difference comes in their body plan. Their shells tend to taper at both ends rather than one or none, which means, unlike land or freshwater turtles, sea turtles can't retract their head or limbs inside their shell, but are much more hydrodynamic in return. Oh, and there's the whole flippers instead of legs thing. These 7 species of turtle are the green, the hawksbill, the loggerhead, the leatherback, the Kemp's ridley, the olive ridley, and the flatback. These 7 are broken down into 2 families. The hard-shelled turtles, which includes every single one of those except for the leatherback, and the leathery-shelled turtles, which includes, you guessed it, the leatherback. Go leatherback having your own family, superstar. Still, all of these species deserve some recognition, so you get to indulge me going through each and every one, telling you a fun fact about that species before we move on. Lucky you! All right, don't give me that look. You've made it to Season 2, so by now you know I gotta give each and every species here their equal amounts of adoration. Come on, it'll be fun. We'll start with the green sea turtle, which is probably the turtle that you think of when the words sea turtle cross your mind. Fun fact, its name isn't actually because the turtle itself is green. In fact, oftentimes it isn't. Yeah, my mind was blown too. The name actually comes from the green color of the turtle's fat, found between their shell and their inner organs. Now, of course, the reasoning behind humans knowing that isn't super fun, but we aren't to the depressing part of the podcast yet, so let's move on. Next up is the hawksbill turtle. And these guys have a really distinctive beak. It's narrow and pointed, kind of like a hawk. Makes sense, right? It's pretty useful for getting into the nooks and crannies of coral reefs to find food, and the food that they eat is another thing that makes this species really unique. They are the only sea turtle species that could, if push came to turtle shove, subsist on a diet composed almost entirely of sponges. Think about that for a hot minute. Could you survive on a diet composed mostly of any one food and still be as happy as a turtle? Didn't think so. From here, we're going to jump to the loggerhead turtle, the world's largest hard-shelled turtle and the second largest turtle overall. Now, the loggerhead's claim to fame is their large, muscular heads and powerful, powerful jaws. These jaws enable it to eat a very unique diet. Instead of consisting mostly of sponges like the hawksbill, loggerhead jaws are powerful enough to crush hard shells of things like mollusks, spiny lobsters, and even queen conch. That is pretty insane. I love a good conch fritter, but the amount of prep work that has to happen for me to eat one is insane, and loggerheads can just go for it. Jealous. Stepping up one size, there's the leatherback. The leatherback. This is the turtle that holds the record for world's largest, reaching sizes of up to 2 meters or about 6.6 feet. Leatherbacks are so pretty and, as mentioned before, are unique in not having that bony, hard shell. Instead, their shell is a carapace covered in leathery skin, lending it a bit more flexibility than the hard shells of their cousins. Oh man, I could almost do an entire episode on leatherbacks, but here's just a few rapid-fire awesome facts. Leatherbacks are the most hydrodynamic of all of the turtles, and they hold a world record for fastest-moving non-avian reptile. They have specialized backward spikes inside their throats to prevent prey from escaping once it's caught. Seriously, check out the show notes for an image of that. It's insane. Also, evolutionarily, leatherbacks haven't changed much in 110 million years, so they're doing something right. They're incredibly long-lived, can dive down to insane depths, and are found almost everywhere as the turtle with the largest global distribution. Truly an amazing turtle. But, as they say, size isn't everything, and there is more than one way to shine. Flipping from largest to smallest, we have the Kemp's Ridley sea turtle. Not even reaching 30 inches, these beautiful turtles are, rather unfortunately, also the rarest sea turtle in the world. Despite the fact that this turtle nests more often than all of the other turtles, the Kemp's Ridley remains the world's most endangered. Uniquely, and unlike other turtles who nest under the pale moonlight, these are the only turtles that actually nest during the day, and they do so in mass nesting aggregations of thousands of females called arribadas. As they grow up, these turtles will actually change color too, going from dark purple to yellow-green as they mature. Now, going a size category up, but keeping with the Ridley name, there's the olive Ridley sea turtle. Just like the Kemp's Ridley, they also nest in massive arribadas, with thousands of females coming together on the same beach to lay eggs. Only the olives do it at night. Olive Ridleys have a unique relationship to humans because of this egg-laying habit, and egg harvest both legally and illegally poses a very nuanced issue. Some sides argue that any harvest poses a threat to the vulnerable species, and others argue that some sustainable legal harvest actually protects the unharvested eggs and leads to increased hatching success. Jury's still out on that one. Lastly, we come to the seventh species, the flatback. These guys are fairly limited in their global distribution, only appearing around the waters of Australia, Papua New Guinea, and Indonesia. And strangely, their nests have only been found in Australia. There's not a lot of data on these turtles. We don't even have enough to know if they're endangered or not, with the IUCN listing them as data deficient. Unlike other sea turtles who swim out into the open ocean, the flatback tends to stick pretty close to shore, finding most of its food in the shallows and eating soft-bodied prey like soft corals, jellyfish, and sea cucumbers. And because we don't know too much about them, that just makes me hungry for more science. All of these sea turtle species are pretty long-lived, and their life cycle is incredible. They hatch at their home beach alongside hundreds of their brothers and sisters, make a mad crawl to the ocean hoping not to get eaten by predators, and once in the ocean, they embark on a decades-long journey to grow up amongst ocean currents and the vast seas, finding food, exploring the world, and learning to be a turtle, all without parental aid. And during this time of adventure, they will travel incredible distances, but when it's time to mate and reproduce, they must travel back to their home beach areas to mate in shallow waters, crawl ashore, lay their own eggs, and ensure that the cycle continues. I mean, epic is the word that comes to mind. But this epic is pretty common to many of our sea turtles and is just the tip of the iceberg when it comes to what makes these species and these individuals truly incredible. I want you to think for a second and try to come up with some other animal that a turtle kind of looks like. It's cool. I'll wait. Can't come up with anything? Me either. This is one of those things that I mean when I say that turtles are unique. There aren't a lot of animals that are even remotely similar to turtles in adaptions, body plans, etc. For this reason, scientists have actually had a hard time pinning down their evolutionary story, and we are only just now starting to come across answers for how, when, and from what ancestor turtles evolved their turtliness. Yeah, that's a scientific term. Who's asking? A lot of this is due, in part, to the fossil record of ancient turtles being really small, at least compared to the fossil records of other species. And until recently, the oldest turtle fossils we had honestly looked mostly like turtles. So, because we have yet to find a lot of fossils with older body plans or lost features, it's really hard to identify what ancestor turtles might have come from. So, as you might expect, there's been a whole slew of theories. Are they closely related to lizards, snakes, and other reptiles, evolving alongside them? Are they older than that, forking off the tree of life as some of the first reptiles? Or are they a truly ancient branch, splitting before the mammal-reptile split, and being unique all on their own? For a long time, the frustrating answer was, who knows? But lucky for us, science tends to be pretty determined when it is thusly denied a satisfying answer. As technology evolves, so too do our investigations. DNA studies, developmental biology studies, and steadily improving fossil records are slowly granting us more answers. With our ever-improving archaeological finds and biological data sets, we have found ancient turtles with teeth, ancient turtles with differing bone and shell structures, and even an animal with no shell but a turtle-like breathing system and turtle-like ribs. All of this begins to point to a more concrete story, that despite how weird and different they are, turtles actually are closely related to other reptiles. Often, turtles are now placed as a close relative of crocodiles and, weirdly, birds. Man, the tree of life is weird. Now, I said before that turtliness is definitely 300% a scientific term, but like any good scientific term, it should probably be defined. So let's do that, huh? Let's talk about what makes a turtle, and we'll start by diving into the huge topic of turtle anatomy and physiology. So if we take that question, what makes a turtle and not some other reptile like a lizard or a snake? To most any other human, one common answer might be, well, its shell, of course. Which is totally right. Maybe a bit reductionist, but totally right. See, it's not just, the shell, but rather it's the shell! The shell is a very complex and really cool structure, and it is a structure of two parts. So when we are talking about the shell, you are not only looking at the dorsal or backside of the turtle like you might think. You are also looking at the flat ventral or belly side, a flat part of the shell called the plastron. These two shell main parts are connected to fully enclose the internal organs of the turtle. And before I go on, I hereby disclose that I am not an expert in anatomy, and the full complexity and story of the turtle shell is much deeper than what I'm about to present. Okay, disclaimer done. Starting with the carapace, that domed back part of the shell, we find that it is actually made out of a fusion of the turtle's rib bones with the turtle's spine. This fusion results in dermal plates, essentially flat bones fused to the spine that flare out and form the basis of the carapace just beneath the skin. I mean, just thinking about an equivalent in human form, just imagine some of your ribcage pushed all the way into your back, fused to your spine, and flattened out into plates so that your back becomes super tough. Trippy. But moving outward from this bone structure is obviously the skin, but that skin is covered in yet more plates, only these plates are made out of keratin, the same material that makes up horns, nails, claws, etc. in other animals. These plates are called scutes, and it's the part of the shell that you can actually see. When you look at a turtle shell, you know how it looks like a bunch of geometric shapes all pieced together with lines in between? Each one of those pieces is a scute. So when you take the hard, bony dermal plates and stack the keratin scutes on top with skin in between, you have one incredible level of protection. Now, this plan is true for 6 of our 7 sea turtles, the only exception, of course, being the leatherback, whose shell is covered by the skin. It doesn't have those scutes. It traded those in for increased hydrodynamics over 110 million years ago. That begs the question, then, if the ribs were used to help fuse and form the bony plates at the back of the carapace, what, then, is that front plate, the plastron, made of? The answer to that, as we understand it, is bones from the shoulder girdle, the sternum, and also sort of, some of the ribs too? Just like the carapace, it is made from these modified bones covered in scutes. Now you can sort of see why I said earlier that turtle anatomy is super unique. What other animal, living or dead, has ribs split to fuse linked shells with the sternum, spine, and shoulder? I think I might speak for a few of us when I say that now, as a human, I suddenly feel somewhat weak in my body plan. Okay, so after the shell, what's the next thing that you want answered about sea turtles? That burning query that keeps you up at night. I know it, you're thinking it, so let's say it together. On the count of 3, ready? 1, 2, I want to know how sea turtles handle salt. What? Not what you were thinking of? Well, it should be. I mean, we all know that seawater is super salty and, well, it's kind of the only available water that sea turtles can drink. Sure, they could get water entirely from their food like some other animals, but they don't. So it's kind of important to talk about how they handle the excess salt. I mean, if humans drink seawater, we'll actually die of dehydration. Maybe if I phrased the question in a more interesting and emotional way. So, how about this? Why do sea turtles cry? Did that get your attention? Now, those among us that are lucky enough to have witnessed turtles coming ashore to lay eggs may note that it appears that they are crying. Why, sea turtle? Who hurt you? Here's the thing, though. Turtles cry almost all the time, even when they're out at sea. And as you probably have guessed, this is the mechanism that they use to avoid poisoning themselves with salty seawater. In order to stay, well, not poisoned, they have to maintain a salt concentration inside themselves lower than that of the surrounding seawater. So it's the tears that they use to shed that sodium. Special glands in the turtle's eyes are constantly pumping salt ions into the turtle's tears, thus enabling them to cry tears that are saltier than seawater. I mean, I've heard a good cry can be cleansing, but this is next level. Interestingly, the tears of the leatherback are different, because of course they are. It's the leatherback. Their tears are almost twice as salty as any other sea turtles, and this is likely due to their favored prey, jellyfish and other gelatinous salty critters, that add to the already high salt load that they have to deal with. Oh, and fun side note, you may have actually already seen this adaptation in action yourself a few years back, because shedding salty tears isn't limited to just sea turtles. Some land and river turtles exhibit this too. Have you seen that video about the butterflies in the Amazon who literally drink tears directly from turtle eyes? If you haven't, I'll post it in the show notes. But yeah, in order to acquire sodium that they need for their own internal workings, Amazon butterflies drink turtle tears. One turtle's toxic tears are another butterfly's source of nutrients. Said it before, I'll say it again. Nature is bloody weird. Looking at how turtles deal with salt, or osmoregulate, you begin to see that being a sea turtle is about balance. And salt isn't the only internal factor in that balancing act. They also, like a lot of other animals, need to thermoregulate, or deal with a fluctuating internal temperature. Most entry-level education teaches us that turtles, just like a lot of other reptiles, are cold-blooded or ectothermic. If you want to get technical about it, which, I do, turtles are poikilothermic ectotherms, meaning that their internal temperature fluctuates as opposed to staying constant, and that temperature is largely driven by the external environment. They have no way to generate internal metabolic heat, and this is why wandering into cold water poses such a risk to these animals. They have no way of warming themselves, and this can lead to one of the most common ways a turtle can get stranded: cold shock. To our knowledge, this poikilothermic ectothermy is the driving truth for 6 out of our 7 sea turtles. They have to very carefully monitor their external environment and water temperatures, using the sun, patches of warmer water, careful active movement, and more. they have to carefully adjust their behavior in order to stay warm. But in biology, there's almost always an exception or addendum to the rule, and in this case, it's a species who I shouldn't even have to name at this point. Here, the leatherback once again stands out from the pack, as it can regularly maintain an internal body temperature of up to 8 degrees Celsius higher than the surrounding water. That's 14-ish degrees higher in Fahrenheit. One study even reported a record internal temp 18 degrees Celsius or 32 degrees Fahrenheit higher than the surrounding water. Longtime listeners, I know what you're thinking. I get it. Obviously, the turtle has to have some internal structure to help capture metabolic energy and throw it back into the body. That's what the tuna does with its wonderful net. I bet the turtle does something similar. First off, good on you for remembering cool tuna anatomy from Season 1. Gold star. After all, it makes a lot of sense. Keeping the heat from the processes of digestion, cell growth, and more, and using that to stay warm. Honestly, for a long time, it actually was thought that the leatherback turtle had a higher metabolic rate of other reptiles of its size, and it captured that heat for its body, much like the tuna did. However, this was debunked as early as 2008, when a review found that the leatherback turtle metabolic rates were actually on par with reptiles of similar size. So, what gives? If the heat isn't coming from metabolism, where is it coming from? Heat doesn't just apparate from nothing, Karen! So, while metabolic capture is an incredibly educated and well-thought-out guess, turns out the leatherback goes about keeping its heat in an entirely different way, merely by being thick with 2 C's. Or, more scientifically, that is to say they can keep heat just by being big and bulky. Turns out, all it takes for these turtles to stay warm is a big body and an active lifestyle. One study pointed to the fact that leatherbacks spend as little as 0.1% of their day resting. The rest of the time, they are constantly swimming. With vigorous swimming comes lots of muscle movement, and with muscle movement comes... BAM! Muscle-derived heat. Talk about a flex. With that heat generated, though, they still have to worry about not losing it to a cold environment, and that's where being big comes into play. With a tiny dip back into the wonderful realm of fish physics, and a little bit of math, it becomes clear that being larger comes with a mathematical advantage. Large, bulky animals have a smaller surface area to volume ratio, meaning that the proportion of area in contact with surrounding cold water compared to the internal volume of the turtle is much smaller than other species. So, as a result, it loses heat much more slowly to the surrounding environment than its brothers and sisters of the other 6 species. Couple this with a few other adaptions of some insulating fat and just a few countercurrent heat exchangers, and you have a turtle who deserves an entirely different term than endotherm or ectotherm. Ladies and gentlemen, you have a gigantotherm. And leatherbacks aren't the only species to use gigantothermy. The most exciting other species to use this technique? Oh, well, only some of the coolest animals to have ever walked this blue-green earth, the mother-freaking dinosaurs. This data on leatherbacks actually helped lend credence to the theory that many aquatic dinos, as, huge aquatic reptiles, employed a similar strategy to stay warm. Now, I'm not saying that leatherbacks are as cool or cooler than the dinosaurs, but I certainly am thinking it loudly. Here's a question. How long can you hold your breath? Okay, if you're doing something important, don't test it right now, but if you're anything like me, you can't do it for much longer than a minute. Heck, I timed myself while writing this episode, and I only got 45 seconds. I'm no freediver, that's for sure. But if I were, I might be a lot closer to being a sea turtle, and if anything, that fact alone might motivate me to practice. But just like us, sea turtles have lungs, and they need to breathe air to, be alive and stuff. And to be honest, they don't have a lot of super crazy adaptations or tricks to extend their breath holding time, like high levels of oxygen-carrying heavyweight myoglobin or crazy lungs that can reinflate after complete collapse, like some seals do. But they can still hold their breath for insane periods of time. There have been recorded times of anywhere from 5 minutes to 45 minutes while swimming and foraging for food. I mean, they took my score and just changed the unit from seconds to minutes. That's not even fair. And that's not all either. That's just while they're foraging and actively swimming. They can hold their breath for hours while sleeping. Breath holding while sleeping. One study recorded a loggerhead turtle making a 7-hour dive to rest. I don't even need to dress that up. That is impressive. So, how do they do this? Now, stay with me here, but this is an area where turtles and human freedivers actually share a lot in common. If you've ever watched any human freedivers talk about how they can hold their breath for insane periods of time, a common thread of the conversation likely talks about the diver's mental state. Many of them emphasize the importance of mental work, in addition to the breath training that they undergo, both of which are important to reach incredible depths on one lungful of air. Being calm and not panicked, anxious, or even excited is important, and if you've ever tested this yourself, the difference is actually pretty incredible. In this way, sea turtles are a lot like human freedivers. The turtle's ability to hold their breath and length that they are able to do so is largely dependent on both the activity they perform while doing so, as well as the animal's stress level during the dive. This plays nicely with the adaptations that they do have, so that in a non-stressed state, the turtle's metabolism actually slows down, meaning less oxygen is required per second. Couple that with large oxygen stores in both the blood and the muscles themselves, and you have one heck of a way to conserve oxygen while diving. This is taken to an extreme when they are resting or sleeping. They are so relaxed that their heartbeat and oxygen consumption slow way down, and they can sleep for hours and hours on a single lungful of air. I mean, one source cited that up to 9 minutes can pass in between turtle heartbeats when they are in this state. It's kind of bizarre to think about, but it's true. The stress level of the animal and the animal's mental state can trigger other physiological changes across several systems, profoundly impacting its ability to hold its breath. Oh, and side note, this is just one of many reasons to never touch wild turtles. Are you tired of talking about turtle physiology yet? No? Great, I really hoped you'd say that, because this next bit is super relatable. Well, for my scuba diving kin, anyways. Sorry, non-divers. But even if you're a non-diver, you've probably heard of one of the more common risks associated with the sport, decompression sickness, also known as DCS, or more commonly, the bends. Really briefly, the risk is that while diving under an increased pressure, the air that you breathe from your tank is more readily dissolved in your body tissues, and if you ascend too fast, these gases can emerge as bubbles in a rather painful way. This can have a range of consequences, from minor joint pain all the way to paralysis and death. Thankfully, this is a rare condition these days. Slow, calculated ascents with decompression and safety stops to let the gas work its way out usually mitigates the risk. For a long time, we classified DCS as a uniquely human problem. After all, shouldn't reptiles and mammals that spend their whole lives diving have some unique physiological adaptation to mitigate such a common risk entirely? But relatively recently, that notion has been challenged. Observations and papers began purporting that diving animals actually can suffer tissue damage and even death from bubbles forming in their veins and arteries, just like the dissolved gases can cause issues in our own bloodstreams. So it turns out turtles might have to deal with the bends just like we do. Now, most recreational human divers don't go much past 40 meters or 130 feet. That's kind of our maximum limit, and we still have to deal with this. And the deepest known diving turtle reached a depth of 1,200 meters or 3,937 feet. I'll give you one guess as to which species set that record. But even the non-record-setting turtles can regularly dive to depths averaging around 54 meters or 177 feet, so they warrant a similar need to ours to expunge the dissolved gases before surfacing. Research into turtle decompression sickness is still relatively new, so this next bit is some healthy speculation, but still the question becomes very interesting. Are turtles resting on the side of reef walls doing the exact same thing that we do, letting that gas buildup escape before they surface? Do they have any extra adaptations to deal with pressure and nitrogen buildup? Do whales, seals, other diving reptiles have to manage their dive profiles carefully in order to avoid sickness like we do? And if so, how do they do it without dive tables or a computer to tell them what's safe and what's not? Honestly, the mind boggles and I want answers, darn it! Man, I cannot wait until we get more studies on that. It's just another thing that we actually share with turtles that we thought we didn't before. But in the meantime, let's talk about something that turtles, well, the hawksbill turtles at any rate, can do that we certainly can't. At least not without a lot of crazy clothing, neon body paint, and UV light. I am of course referring to the 113% confirmed scientific fact that hawksbill sea turtles are some of the sweetest ravers in the ocean kingdom. You might think I'm kidding, but I'm being only 43% facetious here. In 2015, while night diving around the Solomon Islands, a couple of museum science nerds on a quest to find fluorescing coral found something else entirely. A hawksbill turtle that was lit up in red and green lights. This turtle was glowing. Again, I'm going to ask you to check the show notes for a picture of this because it's pretty nuts. Though, I will say that glowing may not be the most accurate or best scientific term, so I guess it would be more accurate to say that the turtle was biofluorescing. That is, it really wasn't generating its own glowing light, but rather taking the light shone upon it and reflecting it back after having changed its color into this dazzling light show. It was only caught because the researchers were using specialized blue lights that were at just the right wavelength to trigger the phenomenon, and it was a scientific first. Hawksbill sea turtles are the first turtle, nay, the first reptile in general, to be known to exhibit biofluorescence. As to the why and the how, well, that's just another mystery. Is it a strategy to attract prey? Is it defense or camouflage? A way to communicate? Does it come from the shell's structure itself or some kind of symbiotic algae? Again, the mind boggles. For now, though, just know that, depending on wavelength, of course, all those sweet lights at your favorite club might just make the hawksbill turtle outshine the most ostentatious raver in aesthetics alone. Their ability to dance, though, less impressive. So, alien-looking lights are pretty cool, but they aren't the only sci-fi superpower that's up these scaly swimmers' sleeves. Sea turtles have another inexplicable ability, and it's one that would make any adventurer, ship captain, or, well, anybody who's gotten lost in a big city jealous. The ability to near perfectly navigate entire oceans worth of distance with a map that exists entirely within the turtle's head. It's kind of like having a GPS installed directly into your brain, in a manner of speaking. We already mentioned that turtles undergo epic cross-ocean migration, subjecting themselves to conditions with no visible landmarks, reduced lighting conditions, and sweeping ocean currents that could throw them off of their intended path. And yet, entire ocean basins are no barrier to them as they travel to find feeding grounds thousands and thousands of miles from the place of their birth. And yet, they can always return to areas that they've previously visited. Now, the level of accuracy varies among some species, but the most well-known example of this is, of course, the female's habit of returning to the beaches of their birth to lay their own eggs. This is usually very close, the same cluster of coastline, but some turtles return to the exact home beach with pinpoint accuracy. Somehow, some way, these turtles know exactly where they are on Earth, as well as the direction towards whatever it is they need, be that mating grounds, feeding grounds, nesting areas. And for a long time, how they did this was unknown. To many scientists in the last 60 years, this was quite frustrating. In one particularly funny example from the 1980s, American zoologist Archie Carr noted that the lack of a credible theory to how sea turtles navigated was no less than a, quote, insult to science. Well, science doesn't take particularly kindly to being insulted, you see. So many scientists got to work trying to figure out the exact mechanisms of this strange ability. And now, finally, today, in the enlightened age of 2022, we can finally confidently say that we have some theories with some decent evidence, but, also we haven't quite pinned it down just yet. Cathartic. Science is wonderful. For real, though, some really cool studies have been done, and we now have a prevailing theory that lends a picture of the answer. Magnetoreception. That is to say that these turtles possess the ability to sense Earth's magnetic field and utilize it as a navigational tool. A bit of a basic explanation that might satisfy the occasional aquarium goer. But this is biodiversity, baby, so you know we're going deeper. The more you look into the physics, the cooler it gets. We all know that Earth is kind of like a giant magnet, right? It generates an intrinsic magnetic field that we can read with special tools, the least of which is the humble compass. But these generated fields aren't uniform. They vary in both intensity and tilt all across the globe. And the turtles can read these two factors to determine their position. So the next logical question, of course, becomes this: how do they do it? Without equipment, these fields are invisible to us humans, but several animals, from turtles to sharks to homing pigeons, all have a demonstrated ability to use these invisible fields to navigate. They must have a mechanism for doing this, so what's the deal? Well, unfortunately, again, we have theories but no real answers. But before you get all mad and go storming off, just listen to how insanely cool some of these theories are. First up, there's the magnetite theory, that posits maybe somewhere in the body are legit mineralized crystals formed of magnetite that kind of function like super advanced compass needles. Magnetite is an iron oxide, so it's magnetic. Actually, it's the most magnetic naturally occurring mineral on Earth. So it stands to reason that these mineral crystals naturally shift their orientation as they move through magnetic fields. This movement forms the basis of the magnetite magnetoreception theory, that this movement is detected by specialized biological receptors, which in turn generate signals that can be interpreted by the brain and nervous system as directionality. Like I said, it's like having little tiny compass needles inside your body that you know how to read just innately. I mean, wow. But the second theory may be even crazier, and it's one that gets hyper advanced. This one is called chemical magnetoreception, and this theory gets down to the molecular level. No, smaller than the molecular level, actually. I'm talking about electrons, those negatively charged subatomic particles and one of the three main components of the atom, usually spinning around the nucleus going all whee! Yeah, those guys. Honestly, I'm not going to claim to fully understand the process of the theory here, but my somewhat surface-level understanding of it goes like this. There's something, maybe light, maybe it's something else, that triggers a transfer of one electron from one molecule to another waiting molecule. Now, this leaves two electrons across two molecules, both of which are unpaired. They don't have a mate. And in this state, both of them spin, kind of like a top, if you want to think about it that way. Then, for a brief moment, they are influenced by the Earth's magnetic field, and their axis of rotation will slightly change. If you want to keep with the top analogy, it's like the wobble of the top as it starts to come to rest. Each of the two electrons in this reaction will wobble at a slightly different rate before returning to their original molecules, which potentially slightly alters them. So the end result is that slight difference in wobble of the electrons due to the magnetic fields could, in theory, be the way that some animals read these fields. I mean, this is literally so small it's subatomic chemical interaction that could be the basis of a system to read magnetic fields. I mean, what? Of course, both of these theories are, at this point, I'll remind you, theories based on some rather interesting data, of course, but finding concrete evidence for either of these systems has proven very difficult. Still, though, interpreting magnetism by mineral magnets or by subatomic particle? You cannot tell me that is not the most sci-fi thing you've ever heard. And it might exist within the humble sea turtle. So, that's, maybe, how turtles read the tilt and intensity of the field that they're in, but how does that translate into a functional navigation system? I mean, if, for example, I could do that, telling me that the field here is pretty strong and tilts slightly up doesn't exactly help me if I'm lost in New York. So there's another part that comes into play. See, in the ocean, these uneven fields of tilt and intensity means that different regions all across this vast expanse actually have unique fields associated with them, a fingerprint or a magnetic signature of sorts. And the turtles, they can learn and identify these signatures. So by reading the tilt and intensity of the field, they are able to use these signatures kind of like a waypoint on a magnetic mental map that they develop throughout their lives. So when you think about it this way, a lot of turtle behavior starts to make a lot of sense, especially when we think about that turtle habit of natal homing, that ability for them to return to almost the exact same place of their birth to have more babies. I mean, it makes sense. As a turtle baby, the first thing you learn is the geomagnetic signature of your home beach, thus enabling you to navigate back there later in life. Aww, baby's first geomagnetic waypoint. There is some really cool evidence that points to this learning happening. But, as the American infomercial might say, but wait, there's more. There's still the question of when. Sounds ridiculous, I know. Turtles only have a few precious moments in the mad crawl to the ocean to learn this waypoint, so when else could it be done? But what if I told you that some of this home map in the turtle's head wasn't fully formed during the mad dash? What if, as a turtle, this map isn't learned early in your life being plucky and adventurous, but rather learned before you were even born? Imagine that. Day one of your life, cresting out of your egg, you already know what home feels like. You have a rudimentary map of it, its waypoint is in your brain, and you are guided by this primal understanding of where to go and what to do. Again, this sounds so sci-fi, but one study published in 2018 posits that this is something that turtles can really do. The evidence from this study demonstrated that any alteration to magnetic fields surrounding loggerhead turtle eggs during their incubation actually had a significant effect on the turtle's sense of direction when they hatched. In fact, all turtles who had their magnetic fields altered from Earth's natural state seemed to just randomly pick a direction to head upon hatching rather than the normal healthy behavior of just heading south, which is what was typical of other turtles in that area. It's some of the first evidence that magnetic environments present during early development while still in the egg actually influence the turtle in life. How crazy is that? Yet, it isn't the only way we know that the environments during incubation plays a role in the life of the actual turtle. In fact, like a lot of other reptiles and fish, sea turtles also determine their gender by their environment. More specifically, the temperature of the sand that they incubate in is the key defining factor of whether or not you become a biologically male or biologically female turtle. Cooler incubation temperatures produce males, and hotter temperatures will produce females. A particularly hilarious way to remember this comes courtesy of my mother, shout out to her, who volunteered at Mote Marine Laboratory's Turtle Watch program for a time. She would always remember it by saying, "Hot mamas, cool daddies," which is absolutely hilarious and ridiculous, but you're totally going to remember it now. All right, there's only one more thing I kind of want to talk about in today's episode, and in order to do so, I'm going to get off track here for just a hot second, but you're going to see why in a minute. So, because I like to cook, I started up this sort of micro hobby of gardening earlier this year. I wanted an herb garden so I could stop wasting time, money, and plastic on buying herbs every time I wanted to cook something fancy. Though, I'll be honest, I hesitate to call it even real gardening. My place doesn't get much sun, so it's one of those real nifty, hydroponic, does-everything-for-you, grow-light herb gardens. I call it my space garden. Since I'm trying to grow 9 herbs at once, though, I learned pretty quickly an important lesson about gardening: the importance of pruning. Man, if I don't cut down some dill almost every day, I'm pretty sure it's going to take over my house. Though it seems kind of counterintuitive, pruning is actually really good for the plant. Removing certain parts allows for the energy to be redirected into new growth, it helps prevent disease, and so on and so forth. Prudently pruning your plants potentially makes them patently more powerful, I say. But because I'm me, and the ocean is on my brain about 97% of the time, I got to thinking, since seagrasses are plants, shouldn't this also be true for them? Look at me, always bringing up seagrass. If you've been a long-time listener of the show, you know how much I adore seagrass. But as plants, shouldn't they also need some kind of natural care and pruning to promote more growth? Looking into it, of course, this is 100% true. Dang, I'm smart. This is where the sea turtle enters stage left. Told you it all makes sense. Sea turtles are one of the very, very few creatures that will eat seagrass, and it's especially prevalent among green sea turtles. I mean, other animals like manatees also eat seagrass, so turtles aren't the only ones, but the species that do kind of act like natural gardeners of seagrass meadows. Just like other plants, cutting it short actually encourages its growth and spread across the seafloor. The mechanism of this is pretty fascinating and doesn't play out like you might think either. If a seagrass bed is not constantly grazed upon, it can actually become overgrown. This will end up overshading the bottom, and older parts of the grass might actually start to decompose. This encourages the growth of slime molds, algae, fungi, and other detrimental blights. Now, the turtles will combat this by actually avoiding eating the blades top down. They will instead target the lower portion of the blade just a few centimeters from the seabed. This gives the turtle a nutritious and unblighted meal, lets those top, older, and more dangerous parts of the seagrass up and float away, thus removing their danger to the bed as a whole, and encouraging the remaining healthy young grass to flourish. This is why some reporting will refer to green sea turtles as the ocean's lawnmowers. And this is only one example of the last thing I want to talk to you about this episode: how turtles play a critical role in the environments in which they live. You've probably guessed it by now, but this criticality earns them the broad title of keystone species. And I just want to touch on just a few more examples of how they play this role in the broader ecosystem. So, In a very similar way to how green sea turtles are helpful to seagrass meadows, hawksbill turtles are super important to coral reefs. The mechanism is just a little bit different, so instead of munching on coral to promote coral growth, they munch on sponges to promote coral growth. I tell ya, Mr. Squarepants best be thankful that he has his pineapple shelter under the sea. Without it, he might be turtle food. See, sponges actually aggressively compete for space with reef-building corals, and if not put in check, there's a very real possibility that reefs would be dominated by sponges instead of corals. And the sponges, squishy things they are actually pretty good at defending themselves from being eaten. Did you know that a lot of marine creatures can't actually penetrate the sponge's exterior to eat them? Or that they produce a bunch of chemicals that actually makes sponges poisonous? Because I certainly didn't until just now. But just like the honey badger, the hawksbill turtle don't care. They'll nosh away on the sponges, all but ignoring their toxins and the glass-like spicule defenses, ripping them apart like they're going to town on some great barbecue. This behavior can actually expose the interior parts of the sponge as well, letting other animals that can't normally get past the sponge's defenses in on the yummy spongy leftovers. And thus the day is saved as the turtles foil the nefarious sponge plot to dominate the reef. What, too dramatic? This next bit is equal parts fascinating, surprising, gross, and just a little bit depressing. But let's talk about every dating profile's favorite activity and go for a long walk on the beach. The next ecosystem that the turtle can play a crucial role in. A bit unexpected, right? After all, turtles really only come on land to lay eggs, or maybe very occasionally warm up in the sun. But even this brief interaction proves to have lasting impact on the beach. Dune ecosystems, aka the beach, are comprised mostly of sand. Like, duh, right? But sand, unlike high-quality potting soil, isn't exactly full of nutrients like nitrogen, potassium, or phosphorus. And yet, as most beachgoers will tell you, many beaches are full of dune grasses and other plants that will need these nutrients. This, of course, is a great thing. Plants stabilize the beach from erosion and promote its overall health, but how can it be that they even grow here? Those nutrients have to come from somewhere. And of course they do, they have many sources, but sea turtles have weirdly proven to be an important one. See, out of the many, many eggs that turtles lay, some do remain unhatched, and those eggs will decompose in the sand, partially adding to the dune's nutrient flow. Additionally, the eggs themselves provide food for beach predators. Birds, crabs, or even lizards will predate upon the eggs or even the poor hatchlings as they crawl from their nests to the sea. At first glance, this of course seems depressing, but sometimes this predation does serve a greater purpose. Eventually, the predators will do what all animals do, and they'll poop. All over the beach. But that defecation produced from their digestion is yet another source of these critical plant nutrients. So while not super directly, this method is another way in which turtles help beach plants grow, stabilizing the beach for the future and adding a luxurious green tone to mix with the blue of the sea and the multicolored hues of the sand. Okay, I get it. It's a little depressing and gross. I mean, let's face it, nobody likes talking about poop or about cute baby turtles being eaten. But that's part of the overall balance of nature. And in the end, this process actually helps the other surviving turtles. A stable and healthy beach is one that future generations of turtles can come back to, lay their own eggs, and ensure the beautiful cycle of life continues for us to appreciate and enjoy. Wow, would you look at me, just rambling on and on about the majesty of the sea turtle. Though, if you made it this far, I would hope that that's exactly what you're here for and what you signed up for. But here's the thing, we haven't even gotten to one of my favorite topics yet, the relationship between sea turtles and humans. That's one of my favorite parts of this show, but sea turtles are so cool. I've already talked about them for well over an hour at this point. So, lucky listeners, we're going to go all tuna fish up in here and bring a whole another episode examining the sea turtle's relationship with us humans. We're gonna turn this into a two-parter. I know, you just want me to keep going. Dane, I hear you say, I'm invested now. How dare you leave me hanging like this? I'm sorry, but for now, I'm gonna have to ask for your patience until part 2 releases. It's gonna be worth it, promise, so stay tuned. In the meantime, I encourage you all to keep shining bright like a glowing hawksbill at night. In hard times, keep your shell up, but always keep swimming forward towards a brighter tomorrow. Because just like the turtle body plan, you are unique, special, and awesome. I'll see you guys next time.